Hello, my name is Marco Kellner, and this is my lab presentation for the oscillations of a mass on a spring. In this lab, we were given a video file to analyze using Tracker. The video consisted of Dr. Greco releasing a small mass to oscillate by the forces of gravity pulling it down and the force of the spring pulling it up. As always, we will be using the fundamental principle of Newton's second law to analyze the motion, and then to model the motion on VPython. In this particular lab, we are interested in the energy principle, and we want to make sure that this principle is satisfied in my model. After having completed the lab, my results were quite favorable because my model followed a path that closely resembled the observed motion, and the graphs showing the changes in energy in my model satisfied the principle. Here's a small preview of what I'll be discussing in this lab. I will try going in the order that makes it the easiest to understand. So now, let's take a look at the major physics components behind this. We know that Newton's second law is the total net force is equal to the mass times the derivative of velocity divided by the derivative of time. And we know that we can use this equation to find the changing velocities for a given motion by a small time step interval delta t. Knowing all this, we want to identify the total net force of the motion, so we have identified that as the sum of the force of gravity and the force of the spring, which is the spring stiffness multiplied by the total stretch. Now let's talk about the energy principle. This principle states that in every object, moving or not moving, the total energy will always be the same. Going by this rule, the change in energy should always be zero. Total energy in an object is defined as the sum of the kinetic energy plus the potential energy. In this lab, there are two potential energies: gravity potential energy, based on the distance of the object from Earth, and the spring potential energy, based on the distance of the mass from the spring. We are going to look at this in terms of the changes in energy. Say for example the mass falls approaching the Earth. The changing potential energy for gravity would be negative, while the changing potential for the spring is positive. So when you add them both up with the kinetic energy, the total change in energy will be zero, and therefore satisfying the energy principle. Let's look at the code that I used to model the motion. To initialize it, I specified the gravity constant of Earth and the spring constant as well as the relaxed length of the spring. These values I got them from the lecture videos because it was literally the same spring. I also specified what the spring force vector and the stretch mean for the visualization. As you can see in this next slide, I specified F grav and F spring and made it so that the net force would equal to the sum of the two. Next, I used Newton's second law in the code so that I could compute the updated velocity and position for each time interval. Lastly, here is the code that calculates the kinetic and potential energies. The kinetic energy K is written as 1/2 mass of the ball times velocity squared because that is always the formula for kinetic energy. The potential energy for gravity is written as the mass times gravity times its position relative to the Earth. And the potential energy for the spring is written as 1/2 of the spring stiffness times the stretch squared. The stretch can be interpreted as the distance from the mass from the relaxed length of the spring. Here's what the model looks like when I run the code. The blue ball attached to the spring is the modeled mass by the code. The red ball is the observed motion from the tracker video. The information for the red ball is put into the code as x, y positions from a CSV file. I put these two balls in the same visualization so that comparing them would be easier. The black arrow is the force of gravity. Notice how it always points straight down and does not change. The blue arrow is the force of the spring and always points to the point of attachment. The arrow, or force, is always changing as the spring stretches and compresses, and this creates the interesting oscillation motion. Now I'm showing you a graph that shows the y position of the model and the experiment as time passes. Notice how they are almost identical for the most part. There seems to be a small discrepancy, making the modeled version arrive at the y position a little later than the observed motion. I believe it is because I missed one time step somewhere in the file, but nevertheless it's not important because the motions are the same. I also got a graph that plotted the changes in energy that I am going to use next in the "what does it mean" question. So for the question, it asks if my model satisfies the energy principle. The answer is simply yes. As you can see in this graph of multiple components, all the changes in energy are shown here. The blue line represents the changes in the kinetic energy as shown. It doesn't change much, and this is to be expected because the mass does not slow down or speed up that much. The red line represents the changes in potential energy for the spring force, and the green line represents the changes in potential energy for the force of gravity. As explained earlier, these two changes are opposite in sign and oscillate as the mass approaches back and forth between the Earth and the point of attachment of the spring. Finally, the yellow line represents the total change in energy, and it's zero because no energy is being added or taken away from our system of the mass, the spring, and the Earth. This satisfies the energy principle. For the second question, here I am showing the oscillations for both the x-axis and the y-axis. I calculated their average periods and they are different. Therefore, if inputted in the formula, they would give different spring stiffnesses. This is because the x-axis oscillation resembles a pendulum, but we want to use the y-oscillation, that is the spring oscillation, affected by the spring force. Thank you for watching this video. I hope you learned something new today.